Async and await might be the two most cargo cult keywords in all of Python. Everybody sprinkles them around, copies the incantation from a tutorial, and prays. And when it breaks, and it always breaks, the error messages sound like ancient prophecy. Coroutine was never awaited. Event loop is already running. Here's the thing though. Async Python becomes almost obvious once you learn one secret. A coroutine is just a function that can pause itself. That's it. Today we're going to build that idea from scratch, with running code at every single step, and by the end, async code will just look like code. And we start somewhere that might surprise you. Not with asyncio. With generators, a feature Python has had since 2001. Because generators are where functions first learn to pause. Let me write one. Count up to n. It loops, and for each number, it yields it. That yield keyword is the star. When the function hits yield, it doesn't return. It freezes. All its local variables, its position in the loop, everything, gets preserved, and control goes back to the caller. Let's poke at it. I'll create the generator, print it, and then drive it manually with next. Run it. And look at the first line. Calling countup to didn't run any code. It handed back a generator object. A frozen function, waiting to be stepped. Each next resumes it until the following yield. 1, 2, 3. And when it finally finishes, it raises stop iteration and smuggles the return value, 6, inside the exception. So burn this picture in. A function that can freeze mid-execution, keep all its state, be resumed from outside, and deliver a final value through stop iteration. Because that, almost exactly, is what a coroutine is. Async await didn't fall from the sky. It evolved, feature by feature, from this humble yield keyword. Don't believe me? Let's catch a coroutine red-handed, with no event loop anywhere in sight. New file. An async function that adds two numbers. And then, the move nobody ever tries. I'm going to call it. Just call it. And print what comes back. And now the plot twist. Coroutines have a send method, just like generators do. So I'll drive it by hand. Send none, and catch the stop iteration when it finishes, exactly like we caught the generators. Run it. Calling add of 2 and 3 gave us a coroutine object. Not 5. No code ran. Exactly like the generator. And then send none pushed it forward. It ran to completion and delivered 5 inside stop iteration. We just executed async code by hand with zero asyncio machinery. This little experiment explains two famous mysteries in one shot. Mystery 1. The coroutine was never awaited warning. It means you built one of these frozen objects and then dropped it on the floor. Nobody ever called send. Mystery 2. What await actually does. Await is just the syntax for run this coroutine, and if it pauses, pause me too, and pass the pause upward. Pauses bubble up the await chain until they reach whoever is doing the sending. And in real programs, the thing doing the sending is the event loop. And this isn't just a cute analogy, it's literally the history of the feature. Before async def existed, asyncio shipped using generators as its coroutines, with yield from chaining the pauses together. Async and await, added in Python 3.5, are dedicated syntax for the exact same machinery, with one extra safety rule. You can't accidentally iterate a coroutine like a list. Same engine, better seatbelts. So let's give the event loop its proper introduction, because it's a much simpler machine than its reputation suggests. At its heart, the loop keeps a to-do list of tasks. A task is just a coroutine that's been wrapped up and scheduled to run. The loop grabs a ready task and calls send on it, exactly like we did by hand. The task runs, pure Python, full speed, until it hits an await that actually needs to wait. Sleeping, reading a socket, whatever. At that point, the coroutine freezes and hands control back, telling the loop what it's waiting for. The loop notes it down. Wake this task in 1 second. Or, wake this one when that socket has data. Timers and I/O readiness. That's what it tracks, using an efficient operating system call under the hood. And whenever something completes, the corresponding task goes back on the ready list and gets resumed with another send. That's the whole engine. One thread, running one coroutine at a time, switching between them at every await. Cooperative multitasking. If you've seen our JavaScript event loop video, this should feel familiar. It's the same architecture. But there's one huge difference. In Python, the switching points are explicit. Code can only switch at an await. Between awaits, your code cannot be interrupted by another task. No lock needed for that dictionary update. That's the superpower Threads never gave you. Enough theory, let's raise something. New file. Here's a fake network call, fetch user. It awaits asyncio.sleep for 1 second, pretending to be a slow API, then returns a user. Asyncio sleep, unlike regular sleep, is a polite pause. It tells the loop, wake me in a second, and steps aside. Now, 2 ways to fetch 3 users. Way 1, the way everyone writes first. A loop that awaits each fetch, one after another. This is the classic async trap, and I want you to see exactly why. Way 2, asyncio.gather. We create all 3 coroutines first, hand them to gather, and await the whole batch at once. Gather schedules them all as tasks, lets them run interleaved, and collects the results in order. And notice the entry point at the bottom, asyncio.run. That's the ignition key of every async program. It creates a fresh event loop, wraps your coroutine into the first task, spins the loop until that task completes, and then shuts everything down cleanly. It's also the answer to a classic beginner crash. You call it once, at the top of your program. Calling it from inside already running async code is where the dreaded event loop is already running error comes from. And the race. Sequential first, 1, 2, 3 seconds. 3.02. And concurrent, 1 second flat. Same function, same 3 calls, 3 times faster. Here's the mental model for why. In the sequential version, each await fetch user freezes the main coroutine until that one fetch completes. The waits happen back to back in single file. Async syntax, synchronous behavior. In the gather version, all 3 sleeps start together. The loop has 3 timers ticking at once, and all 3 tasks wake up at the same moment. The waiting overlaps. That is the entire value proposition of asyncio in one sentence. It overlaps waiting. Now let's zoom in on how tasks actually get scheduled, because there are some genuinely surprising details in here. New file. A worker coroutine that announces it started, sleeps for a given delay, announces it woke up, and returns its name. In main, I create 2 tasks with asyncio.createTask, a slow one, 2 seconds, and a fast one, 1 second. And right after creating them, I print, nothing ran yet. Then, the subtle line. Await asyncio sleep 0. A sleep of 0 seconds. Looks pointless, right? It's one of the most idiomatic tricks in async Python. It means, dear loop, I yield, run whoever's ready, then come back to me. Watch the order of these prints carefully. Creating tasks. Tasks created, nothing ran yet. So create task schedules work, but doesn't run any of it. Then our sleep 0 yields once, and boom, both workers print started, back to back. One single yield, let the loop sweep through its entire ready list. Then fast wakes at 1 second, slow at 2. In wake-up order, not creation order. But look at the results list. Slow then fast. Gather preserves the order you pass things in, regardless of who finished first. Which is exactly what you want, results you can zip back to your inputs. And one hard-earned warning from production code. Keep a reference to your tasks. If you create a task and forget it, the loop only holds a weak reference, and the garbage collector can vanish at mid-flight. Fire and forget in asyncio needs a plan. Now for the dark side. One single innocent-looking line can silently destroy everything asyncio gives you. And this exact bug ships to production constantly. New file. Same fetch function as before, same gather of 3 calls. One difference. Instead of await asyncio sleep, someone wrote time.sleep. Regular, synchronous, blocking sleep. Maybe it's hiding inside a library they imported. Maybe it's a database driver or requests.get. We're still using gather. The code still says async def. It still awaits. It looks exactly like our 1 second version. Run it, 3 seconds. All the concurrency, gone. Why? Remember the engine. 1 thread, and tasks only switch at an await that actually yields. Time.sleep never yields. It grabs the one and only thread and holds it hostage for a full second, while the event loop, the timers, and every other task just stop existing. Nothing can switch, because switching is cooperative, and this code refuses to cooperate. In a real server, this is one endpoint with a blocking call freezing every other request in the process. The scariest part is that it works fine in testing with one user. So what do you do when you're stuck with blocking code? Some ancient library, no async version, but you need it inside your async app. Since Python 3.9, the clean answer is asyncio.gather. New file. Here's our legacy blocking fetch, plain def, plain time sleep, completely unfixable. And in main, instead of calling it directly, I wrap each call in asyncio.gather. That ships the blocking function off to a worker thread and hands me back an awaitable that completes when the thread finishes, which means I can gather them like any other async work. Run it, 1 second. Concurrency restored. The 3 blocking sleeps ran in 3 separate threads. The event loop stayed free the whole time. And if you remember our GIL discussion from the Python internals video, threads waiting on sleep or I/O release the lock, so they genuinely overlap. Blocking code belongs in threads. Async code belongs on the loop, and to thread is the bridge between the two worlds. One more superpower, and it's the one that made me love asyncio. Cancellation. Killing a thread in Python is somewhere between painful and impossible. Canceling a task is one method call. New file. Here's a flaky API that takes 10 seconds. Way too slow, and we're not going to wait for it. Defense number 1, asyncio.waitFor. Wrap the coroutine, give it a deadline of 1.5 seconds, and if it blows past that, we get a timeout error, and crucially, the task itself gets canceled. No zombie work left running behind our backs. Defense number 2, manual cancellation. Create the task, let it run a moment, then call task.cancel. That doesn't yank the rug out instantly. It arranges for a canceled error exception to be raised inside the task at its next await. The task gets a chance to clean up, close its files and connections before dying with dignity. Run it. Gave up after 1.5 seconds. Canceled by hand. Both defenses worked. And this is a genuinely big deal, structured control over runaway work. Timeouts on everything, cancellation that actually cleans up. If you've ever tried to abort a hung thread, you know exactly how luxurious this is. And if you're on Python 3.11 or newer, there's an even nicer pattern built on top of this, task groups. You open an async with asyncio.taskGroup block, create your tasks inside it, and the block guarantees that when it exits, every task has either finished or been canceled and awaited. And if one task fails, its siblings get canceled automatically. No orphan work, no leaked tasks, ever. It's called structured concurrency, and once you use it, Gather starts feeling like the low-level tool. So let's settle the eternal question. Asyncio, threads, or processes? Here's the honest decision guide. Is your workload mostly waiting? Network calls, AP is, databases, thousands of concurrent connections? That's Asynsio's home turf. Tasks cost almost nothing. 10,000 of them is routine, and the explicit await points make the concurrency visible and mostly race-free. Is it waiting, but through blocking libraries you can't replace? Threads, or Asyncio with toThread as the adapter? A few dozen threads waiting on I/O is a perfectly respectable architecture, and often simpler. And is it actual computation, number crunching, parsing, image processing? Then neither helps. One thread, one GIL, remember, you want processes or a library that releases the lock. This decision tree is also a map of the modern Python ecosystem, by the way. Fast API and its underlying server run your endpoints on exactly the event loop we just built up. HTTPX gives you awaitable requests. SQL Alchemy grew a full async mode for databases. Discord bots, trading systems, web scrapers pulling thousands of pages. That whole world runs on the machinery from today's video. When those docs say async all the way down, you now know precisely which machine they're talking about and what it costs to block it. And one closing rule of thumb, the async contagion rule. Async spreads upward. If a function awaits, its caller must be async, and so on, all the way to the entry point. Which is why the sweet spot for Asyncio is at the edges of your system, servers, clients, scrapers, bots, where the concurrency lives, not sprinkled randomly through your business logic. Choose it because you're waiting a lot, not because it's trendy. Let's replay the whole journey, because it's one straight line. Functions learn to pause with yield. Coroutines are that same trick with nicer syntax. Frozen objects driven by send. We did it by hand. The event loop is just the machine that sends, tracks timers and sockets, and resumes whoever's ready. On top of that, gather overlaps your waiting, tasks are scheduled lazily and cancel cleanly, and the one commandment is, never block the loop. Time.sleep, requests, heavy computation, they all belong into thread or a process pool, not on the loop's thread. Every demo you saw is tiny, self-contained, and worth retyping yourself, especially the coroutine.send one. That's the one that rewires your brain. If Asyncio finally clicked today, a like genuinely helps the channel, and subscribe for more deep dives like this. Next time, we're taking one real query from 3 seconds to 3 milliseconds, live, with SQL indexes and query plans. See you there.